Thank you all for joining the meeting. A very warm welcome to all the respected faculty members, research scholars, and postgraduate students joined and who will be joining us today. We are delighted to have you all with us for the second day of the AICT ATL sponsored 6-day online FDP on AI/ML based reconfigurable antenna design for next generation wireless communication. Today's session focuses on reconfigurable antenna design, and we are privileged to have Professor Arun Kumar from NIT Warangal with us to share his valuable expertise. A brief introduction about Professor Arun Kumar. He is an assistant professor in Department of Electronics and Communication Engineering at NIT Warangal, holding a PhD from Jawadhpur University. His core teaching portfolio includes courses such as antenna and propagation, RF system design, radar engineering, substrate integrated waveguide circuits. His research interests in microwave and millimeter wave passive and active circuits, reconfigurable antennas and filters, RFIC design, metamaterials, and time-modulated RF circuit. In his research, Dr. Arun Kumar has been actively engaged in nearly 11 sponsored projects for the tune of about 10 crores. In that, nearly 5 crore project has been completed. Now he is currently having a project greater than 5 crores. For example, he is the principal investigator for design and development of a W-band front-end for imaging application using silicon germanium technology from DST-SER for a tune of 37 lakhs, and feasibility study of a dual-band communication front-end from NIT Warangal for a tune of 5 lakhs have been completed. He is currently leading 6 projects. 2 among them are design and development of an analog front-end at 210 to 255 gigahertz for 6G application for a tune of 2 crore from DOT TTDF scheme, and time-modulated antenna array system for automatic beam steering towards user target for 6G communication from DOT TTDF for a tune of 50 lakh, among other ongoing projects. Beyond teaching and funded project, Professor extends his scholarly output and outreach. He has published in high-impact factor journals such as IEEE Transaction on Microwave Theory and Techniques, IEEE Microwave and Wireless Components Letters, IEEE Access, and the Journal of Electromagnetic Waves and Applications. He also supervises PhD students in advanced topics of antenna design, RFIC, and metamaterial systems, and frequently conducts workshops, and he acts as an expert person for various technical sessions, FTP, to bridge academia and industry. Thank you so much, Professor, for accepting our invitation. We extend a warm welcome to you. Despite being currently abroad to participate in an international conference, he graciously accepted our invitation and made time to interact with us today. Thank you, sir. Over to you, sir, for today's session.
Thank you very much, ma'am, for the introduction. Good evening to all participants. First of all, I would like to thank the coordinators for giving me this opportunity to take this session on reconfigurable antennas. So I'll not delay. Once again, warm welcome to all the participants for this 6-day faculty development program on AI/ML-based reconfigurable antenna design for next generation wireless communications, organized by Karunya Institute of Technology and Sciences, Tamil Nadu. Myself, I'm Dr. G. Arun Kumar, working as assistant professor in the Department of ECE at National Institute of Technology. So today, I'll be briefly going through what do we mean by reconfigurable antenna, its applications, then followed by what are the different ways in which people design these reconfigurable antennas, and the basic criterion that is required for reconfiguring a particular antenna. So we'll be emphasizing on microstrip antenna because that is the antenna that most of us generally design and develop because of its planar nature. So we'll be concentrating on applications of reconfigurable antennas, followed by microstrip antenna, how we are going to design it, and what are the feed points, and how we are going to design those feed points, followed by the equivalent circuits for the pin diode and varactor diode. And then we'll see some examples how reconfigurability has been achieved for various parameters of the antenna. Then we'll move on to the hands-on session. Coming to reconfigurable antenna. What is the need for these reconfigurable antennas? So if you see, whenever we are looking at a system, for example, if you are taking our mobile itself, it has several systems included in it. Like you have your Wi-Fi, you have your mobile, which is communicating through your GSM channels. Then you have your Bluetooth and other connectivities. However, if you see, if you want to make a system compact, then the requirement that we have is all these bands, whatever we are seeing, like your GSM or Wi-Fi or your Bluetooth, they work at different frequencies. And looking at the miniaturization that is happening in these systems, we want everything in our palm, right? So if that is the case, then making systems compact, we need to merge or have multifunctionality for the components that we are designing. So, and if you are looking at any system, what we see is the passive circuits, that is your filters, your dividers or your couplers, along with your antennas, are the components that take most of the area on your systems. Like if you want to design a receiver, the receiver will be coming in, say, few mm by mm, like 1.5 mm by 2 mm or so. The complete receiver chip comes, and then once it is packaged, it generally happens in QFN package. So the maximum dimension would be 3 mm by 3 mm, or 4 mm by 4 mm, or 5 mm by 5 mm. So your entire receiver and transmitter comes in mm's, whereas when it comes to using the antennas and passive circuits, the sizes are dependent on the wavelength at which we are operating. And multiple antennas implies we require larger area. So people have been moving into, into areas wherein they can include multifunctionality into their system, right? So one such area where people require these multiband, wideband, and reconfigurable antennas is your wireless devices. And second one is your cognitive radio systems, wherein you want to switch between different channels, and the switching has to be fast so that you do not lose the communication. So now, when we are looking at the reconfigurable antennas, we are broadly dividing this into two categories. One is your IoT devices, wearable and implantable wireless devices, and 5G and millimeter wave systems, where we can go for reconfigurable antennas. The other sector is your automotive radar, satellite communication, cognitive radar, and communication and sensing. So we have several applications wherein we require the antenna to be reconfigurable. Reconfigurability implies not only in terms of its frequency, it can be in terms of its pattern, it can be in terms of its polarization, and so on. So coming to reconfigurability, the reconfigurability can be in terms of your frequency, pattern, and polarization. So how are we, or where are we going to use these frequency resonant antennas? So basically, we want these frequency resonant antennas to replace multiband antennas, wherein you are designing a multiband antenna. The issue that you might face spurious bands as well. So controlling your multiband frequencies becomes difficult for you, and this is important because you, whatever frequencies that enter into your system act as intermodulation products for your system, and then they saturate the subsequent stages in your system. So you don't want unnecessary frequencies entering into your system. So by using a reconfigurable antenna, you can tune your antenna to multiple frequencies, and hence multiband effect can be achieved with reconfigurable antennas. Second thing is replacing wideband antennas, wherein uh, the issue is once again you're picking up of spurious signals that are coming from other systems. Like if you are choosing a frequency in ISM band, say 2.4 gigahertz, and you have several systems working around 2.4 gigahertz. So if you are having an antenna which works from say 3 gigahertz to 10 gigahertz, then you'll be having multiple such bands which where the frequency is being radiated, and we need to make sure that these frequencies do not enter into our system, or at least we need to make sure that even if they are entering, the energy that is coming from these systems is not amplified by the system, so that intermodulation products do not come into picture in your system. Then these are used to decrease the complexity of hardware, wherein we are reducing the number of antennas by tuning the antenna to a required frequency. So hardware complexity gets reduced by tuning, wherein we are using simple pin diodes or varactor diodes to tune the frequency or pattern or polarization. And then moreover, it can be also used for improving the performance of wireless system by saving energy and space. So if you are looking at pin diode, the current that it takes is 10 milliamperes with a voltage of 5 volts. And in fact, the amount of current that is dissipated in the off state is 0. And if you consider your varactor diode, because it's operating in reverse bias, so it doesn't draw any current from the DC supply. And hence, we can say that these circuits can be operated with minimum energy requirement from the battery. Coming to the microstrip antenna, most of you might be knowing, but I'll just briefly cover this topic. So your microstrip antenna consists of a bottom copper layer, which we call it as ground plane. Then we have a dielectric material over the ground plane, and this dielectric material generally separates the uh, top copper plate from the bottom copper. And the top copper is where we design the patch, which radiates the energy. And this configuration helps us to integrate our antennas with circuits. And hence, microstrip antenna has become popular. And if you are using a substrate which is flexible, like you are going for a 10 mil substrate or a 5 mil substrate, then conforming this microstrip patch to a given surface also becomes easier. And hence, microstrip antennas have been widely used in our systems. So we have several different shapes for these microstrip radiators. They can be rectangular in shape, square, pentagon, ellipse, circle, or they can also be forming a loop. It can be triangular, it can be rhombus, it can be biconical, and so on. Right? You take up a patch, whatever shape it might be, and if you are providing the requisite feed to that, it starts radiating. So each of these structures have their own advantages, so and also disadvantages, and depending on the requirement, we choose a particular shape for the antenna. So the advantages of microstrip antenna: it's low profile, and it is also conformable, so it can be used in most of the cases, and it is easier to fabricate, unlike other antennas like your waveguide based antennas or your wire based antennas. Fabricating microstrip antenna is very easy. What we require is either a CNC milling machine or etching and photolithography for fabricating the antenna. Feeding wise, once again, the feed is very easy. We can use a coaxial cable or a microstrip line for feeding these microstrip antennas. Unlike your wire antennas, where you require a balloon to be used to match the instrument impedance or your transmitter receiver impedance to the dipole or your wired antenna impedances, which slightly complicates the design of your dipoles. Then they are easy to integrate with other microstrip elements and also systems, because most of your microstrip circuits are done in your PCB, which is nothing but a microstrip based lines. So integrating with them becomes easier, unlike your waveguide based or wire based antennas, where you require a transformer which transforms the microstrip impedance to the waveguide, and then transitions that into the required modes in which the waveguide is transmitting. Then coming to the pattern, the typical pattern that we get for the microstrip antenna is hemispherical, right? So most of it is being radiated in the broadside direction, and the directivity typically varies between 6 to 8 dB. And then when we want to make an array so that the beam width and gain performances are improved for an antenna, we it becomes easier for us to work with microstrip patch antennas. And the disadvantages that we have is with respect to the bandwidths. So the typical bandwidths that we get with your normal microstrip patch antenna is about 10 to 20%, which may not be sufficient for us in certain applications. Moreover, the microstrip patch antenna bandwidths can be controlled or can be varied with respect to the substrate dimensions and the permittivity that is being used by the substrate. Then the efficiency of these antennas is lower because of losses it offers. Like if you are going for a waveguide based antennas, the only loss that you have is your conductor loss, whereas when it comes to your microstrip antenna, the losses that we are going to have are both conductor as well as dielectric, and depending on the thickness of the substrate that you are taking, the uh, there is one more loss which we call it as surface wave loss. Instead of the fields being perpendicular, they start propagating in the longitudinal direction, giving rise to surface waves. And the energy is distributed from the fields that are radiating into these surface waves, and hence the efficiency of the antenna is reduced. And then as the frequency is increased, the dimensions of your antenna become smaller and smaller. So if you want to go for very high frequencies, then fabrication may be an issue for us. And if you are going for lower frequencies, then the dimensions become too large, because the minimum dimension that we require for the microstrip antenna to radiate is lambda by 2, right? So typically, microstrip antennas are used up till your millimeter waves. Beyond that, the losses offered by the dielectric and conductor become more. So instead of radiating, most of the energy is still stored in the substrate itself. So people generally move on to different sort of antennas, like your substrate wave integrated antennas, wherein the substrate is being used as a waveguide by shorting the top and bottom ground planes. And then coming to power handling capabilities, the microstrip patch antenna power handling capability is not very high, wherein if you want to use these antennas where in kilowatts of power needs to be transmitted, that may not be possible with microstrip antennas because of the dielectric breakdown, lower dielectric breakdown of these substrates. So these are the some of the disadvantages that we have with respect to microstrip antenna. So whenever we are choosing an antenna, we need to look into several parameters apart from whatever we generally do for our systems, like the resonant frequency of the antenna, then axial ratio, what is the beam width, what is the bandwidth requirements. We also need to keep other factors into our mind when we are designing these, like whether what are the losses that we are going to encounter when we are designing at a particular frequency, then whether the substrate height, whatever we have taken, results in surface waves or not, and then what would be the power handling capability of the or what is the power that the antenna has to transmit or receive. Then coming to the different types of feeding, we have a coaxial feed, which is the typical feed for single patch antennas, wherein we are having the patch, and these and this is the radiating slot, which means uh, the radiation is happening from this direction and this direction, and both of them combined, and you are going to get a broadside pattern, right? So this is one radiating slot, and this is another radiating slot. And if you see, the feed is generally kept at the center of the width. This is done so that you are getting linear polarization for the antenna. And if we typically see the electric field pattern, whatever we are going to have for the antenna, so we are having top copper, we have substrate and bottom copper. So this is the bottom copper and this is the top copper. So whatever fields that we have, you have maximum field here and maximum field here, because this part and this part, they are open circuit. Because they are open circuit, electric field is maximum at open circuit. And then if you see, the typical length that we take for this is lambda by 2, or in fact lambda g by 2. So you are having two maximas at the edges, so there exists a minima at the center. So here, if you are looking at this point, we have maximum impedance, right? This point and this point, and at the center of the patch you have minimum impedance, right? So now, whenever we are connecting this coaxial feed line, we need to choose a point where the impedance is 50. So here we are having minimum, here we have maximum. So we need to choose a point where the impedance is 50 ohm. So it lies somewhere in this particular region. So in order to do that, we generally use a formula which is given by this, where R is the impedance which you require it to be 50 ohm. RH is the open circuit impedance of the patch antenna, right? And then pi x naught by L, where your x naught is the feed position at which the impedance would be 0, and L is the length of the patch antenna, right? So using this expression, you will get an approximate value where the impedance, or the position at which the impedance is 50. So once you get to know the impedance at the open circuited edge of the patch antenna, this R is 50 ohm, this is the impedance, open circuited edge impedance. So, and then L is already known, the only unknown is x naught. So we'll solve for x naught and then get the value of x naught and substitute or put the pin at that particular position. Now, why we have considered this as 50 ohm? The reason being, most of the measurement equipments that we have are standardized to 50 ohm. And once again, why these are standardized to 50 ohm? These are standardized to 50 ohm because your 50 ohm impedance is a compromise between your losses and power handling capability. So if you see, people have done experimentations wherein they have seen that if the impedance is 30 ohm, the power handling capability of that particular transmission line is highest. And if the impedance is 77 ohms, then the losses in that particular transmission line are minimum. So if you see, if you are taking a average of these two values, we end up close to 50 ohm. And that's the reason your 50 ohm is a compromise between your power handling capability and your losses in the transmission, right? So now we are using a coaxial feed, and the impedance of that we are considering it as 50. So that's the reason we are considering R as 50. So coming to the advantages and disadvantages of your coaxial feed, the advantages are it's simple, directly compatible with coaxial cables, easy to obtain input impedance by adjusting the feed position. Disadvantages being as the substrate height increases, because we are using a thin wire here, which we are calling it as pin, for thick substrates, this gives rise to parasitic inductance, which may interfere with the field distribution that we are having in the patch antenna. Then if you are going for arrays, then it may not be easy for us to have multiple coaxial connectors to be connected. So we move on to the next feed, which is inside feed. And here, if you see, instead of the coaxial feed, we are having a microstrip line. The impedance of this microstrip line is 50 ohm. And once again, we are finding a position where the impedance is 50. And we need to make sure that whatever CPW line or coplanar waveguide line that is formed here, that also has 50 ohm. So how are we going to do that? Here, this is 50 ohm line. And then whatever impedance on the patch we are having, that is also 50. And then we need to choose the gap. Width is fixed, so we need to vary the gap of the CPW line to make the impedance as 50. And once we make that, then the return loss of our microstrip feed improves. So coming to the advantages, it's very simple. Once again, we do not require a pin to be inserted from the ground plane, but it's planar feeding. And then it is easy to use for arrays, because being the feed line is planar, so it's easier for building arrays with microstrip feed line. And then it's easy to obtain input match. Disadvantages being, if the thickness of the substrate is more, the width of this line is more, and then it starts radiating. And second thing is that when we are having these notches as deeper, then the current distribution on the patch is distorted, and hence the radiation pattern is also distorted. And once again, the formula that you are seeing here, the formula that we are seeing here is similar to what we have seen for your coaxial feed. So once again, Rn is the input impedance for the patch that you are going to have. X0 is the position at which the patch is having 50 ohm impedance. L is the length of the patch, and A and B are two coefficients which need to be calculated from this particular paper, right? So it's very much similar to that of your coaxial feed, and getting the 50 ohm points. Once you get the 50 ohm point, then matching it with required width of the microstrip line so that you get good return loss. Then there are other ways of feeding the patch. If you see, the earlier two feeds are narrowband feeds, wherein the bandwidths that you typically get is between 10 to 20%. But if you are looking for a wider bandwidths, then aperture coupled patch antenna is typically used. Wherein, once again, if you are looking at the configuration, on top you are having the patch. For this particular patch, you are having the ground plane, and you have a slot in the ground plane. On to the other side, you are having the microstrip feed line. So by doing this, one thing that we are doing is we are separating the feed line from the patch. So whatever spurious radiations that we had from the microstrip line are not interfering with the patch radiation. Second thing, because of the transition that we are having between your microstrip line and slot line, the bandwidth enhancement takes place, and you are going to get a wider bandwidth. So here, if you are looking, whenever we are designing the microstrip patch antenna and your feed lines, there are two contradicting requirements for the microstrip feed and your patch. For your patch, you require the substrate height to be more and dielectric constant to be lesser. Whereas for your feed lines or your microstrip circuits, you require your epsilon r to be higher and substrate thickness to be lower. The reason being, when dielectric constant is higher and substrate thickness is lower, most of the field is within the substrate. But in case of your patch antenna, what you want is the fields to be radiated into free space. So you want your epsilon r to be lower and substrate height to be higher, which helps in radiating. So here when we are separating the two substrates, we can use higher dielectric constant for microstrip line, so radiation is minimized. And moreover, the ground plane separates your microstrip line and patch, so spurious radiations are reduced. Coming to disadvantage, we have to go for multi-layer fabrication, and there may be an issue with alignment of this feed lines with the proper patch antenna feed. So how are we going to design this microstrip patch? So once we know the frequency at which we need to design, we take that particular frequency, then we'll choose the mode in which the microstrip antenna has to work, and then see epsilon effective. So basically, your root over epsilon effective is taking care of the effective dielectric constant because the fields are extending both into free space and your substrate. You require an epsilon effective dielectric constant to be taken care of. And then if it is in free space, we take it as length L, which is obtained as lambda by 2. But if it is in over a substrate, then we need to take the effective wavelength, which is represented by root over epsilon effective. So the frequency that we want to operate is given by this particular formula, and here delta L represents the fringing fields. So these fringing fields are happening at the edges of your patch, wherein they are extending the length of the patch antenna. So if you are not taking care of the fringing fields, then whenever you are designing an antenna, then it resonates at lower frequencies, and once you reduce the length, then the resonant frequency moves to the required frequency. So that change in length is coming because of the fringing capacitances. And these are the formulas that we generally use for designing the patch antenna and getting the required values for the parameters for a given substrate parameter. So we have few observations here. So whenever we are going for the design of antennas, we typically keep the substrate thickness as h by lambda naught equal to 0.02, and the permittivity is about 2.2, and this results in a bandwidth of about 3%. And if you are using a thicker substrate, then the bandwidth can be achieved is 10%. And we may require, if you want to extend the bandwidth, we may require special feeding techniques like your aperture coupling and stacked patches. So after looking at the microstrip patch antenna, the next topic that we need to have an idea before we move on to reconfigurable antennas is your diodes. So whenever we are designing reconfigurable antennas, typically we use two types of diodes. One is a PIN diode, second one is a varactor diode. And people have used transistors as well if they are designing on MMIC instead of diodes. So if you are looking at a discrete implementation, then these are the two diodes that we typically use. And in case you are not much concerned about the isolation between on and off state, there is one more diode that we use, which is your Schottky barrier diode. So whenever we are looking at this Schottky barrier diode, it is used in place of pin diodes. The reason being, the switching speed of your Schottky barrier diode is much faster than pin diode. So, however, in this particular lecture, we'll be concentrating on pin diode and varactor diode. So, coming to pin diode consists of three semiconductor layers. First one is P-type semiconductor. Second one is N-type semiconductor. So, in our typical diodes, we have P and N in the diode. In PIN diode, we have one more semiconductor, which is intrinsic semiconductor, which is devoid of any charge carriers. And this intrinsic semiconductor is responsible for us to get high isolation between on state and off state. So what happens whenever we are forward biasing this, the holes from the P region enter into the I region, the electrons from N region enter into the I region. And now when the diode is forward biased, I region is filled with charge carriers. So it presents a short circuit for the current to flow from your positive terminal of the battery to the negative terminal of the battery through pin diode. And you are going to have a resistance that is offered by the PIN regions, which generally is the equivalent circuit that we take when the diode is in on state. And when the diode is reverse biased, the whatever charge carriers that have been present in the intrinsic region when it was forward biased are pulled by the battery terminals to their respective terminals. So the electrons are pulled by the positive terminal, and the uh, holes are pulled by the negative terminal of the battery, and then the I region becomes devoid of carriers. So it presents a capacitance. So because it's devoid of carriers and P and N act as plates for the capacitor, and I region acts as a dielectric, so it acts like a capacitor. So in off region, we generally consider the pin diode to be in to provide a reactance of capacitance. So now, if you are looking at the equivalent circuit, here we are seeing the diode, and this diode can be a resistor or a capacitor, or we can have variable capacitance and variable resistance. To some extent, variable resistance, it generally does not vary much, but it can be variable capacitor depending on the voltage that we are giving at the terminals of the battery. So now this is an ideal diode that we are considering, wherein in on state we consider this to be a resistance, in off state we consider this to be a capacitance, as shown here. So in on state we are considering this as a resistor, in off state we are considering this as a capacitor. And the reason why we are considering this like resistor and capacitor, we have just discussed a few minutes back, how your diode behaves in on state and off state. And now whatever additional components that you are seeing here, like you are seeing a capacitor here, an inductor, and a resistor. So whatever connections that you are having, because if you are seeing your diode is not just a diode. So inside, when you are having your diode, you have your base, then so you have your pin diode looking similar to this, wherein this is the area of the pin diode. So now when you want to connect this, or whatever package that you are having, you are using wires to connect this to the package, right? So these wires, whatever are being used, they give you inductance. They give you inductance. And because these wires are placed closely, and because of the close placement of these wires, you are going to have a capacitor between them, which leads to parasitic capacitance. And this capacitance can also be coming from the, this is how your single pin diode looks, wherein the inductance is because of the bond wires that you are using, and also because of these leads. So these leads give you inductance. And if you flip this, they come like this. So you have a potential difference between these two. There is a capacitor here as well, right? So that's how this represents your package parasitic. This and this both result in your package parasitics. And this is the losses that you are going to get when your current is flowing through your semiconductor as well as your leads, right? It can be because of your ohmic losses or your bulk junction or bulk semiconductor losses that you are getting, right? So if you are seeing, the only parameter that is changing here is your diode, resistance, and capacitance. These parasitic things are remaining same for your diode in on condition and in off condition. Now, coming to varactor diode. Varactor diode is similar to that of uh, your pin diode, but the difference being your varactor diode is a PN junction diode, highly doped PN junction diode, which is only reverse biased. It's not forward biased. It's used in reverse bias condition. So if you're looking at the equivalent circuit is more or less similar to that of your pin diode, but the only way the diode behaves is different. So now diode is behaving like a variable capacitor. As you are reverse biasing this, the depletion region in your diode is increasing, because of which the capacitance decreases. So as you are increasing the reverse bias voltage, the capacitance decreases. And hence you are representing the diode as a variable capacitance. And because it's being reverse biased, the impedance of the varactor diode is changing, and hence the resistance value is also changing with respect to voltage. And once again, your CP and LP are package parasitics. And here you might wonder, we haven't included the resistance. Now, because the diode is reverse biased, and this resistance, diode resistance, and the resistance, ohmic losses resistance, or your bulk semiconductor resistances are coming in series, it becomes negligible. And hence, your variable diode, reverse biased diode resistance is much, much more than the ohmic resistance that you are having here. And there is one more way of implementing your reconfigurability, that is using your MEMS switches, which is a mechanical switch. So if you're looking here, we are having two types of switches for MEMS. One is your resistive switch, second one is capacitive switch. So in your resistive switch, what you see is you are having your input terminal and an output terminal, and there is a cantilever that is extending from your input terminal to the output terminal. And by applying a voltage across your terminal 2, you are pulling this cantilever towards it, and once it is pulled down, there is a connection which results in a switch being on. And when the fixed voltage is changed, the cantilever, there is a gap between the cantilever and your pin number 3, and the switch is in off condition. And if you're looking at the capacitive switch, basically there is a direct connection between your input and output, unlike your resistive switch. But then you are open circuiting or short circuiting it by pulling the membrane towards pin number 2 by applying a voltage. So these are the two ways of implementing your MEMS switch. So coming to which diode or where we are going to use which switches. So if you're seeing, for pin diode, the bias voltage required is 5 volts, MEMS diode 20 to 90 volts, varactor diode 0 to 30 volts, right? So these are the voltage requirements that we have. Bias current, if you're looking, pin diode takes about 10 milliamperes of current. It can typically extend up till 100 milliamperes, depending on the power handling capability of your diode. As well as it also depends on power handling capability of the diode, also depends on the reverse breakdown voltage, apart from the forward bias current. Then we are having MEMS where bias current is 0. For varactor diode also, bias current is 0 because it's reverse biased. Bandwidth, if you are seeing, because your pin diode at lower frequencies may give you good bandwidth, but as the frequency increases, because of the parasitic capacitances and inductances, the bandwidth is narrow. MEMS, it's generally broadband. Varactor diode, once again, because of the parasitic capacitance and inductance, the bandwidth is narrow. Looking at the insertion loss, typically pin diode provides you about 0.5 dB, MEMS 0.2, and varactor diode 0.5. Isolation that you are going to get is these values are for your single diodes. So 10 to 20, 20 to 40 for MEMS, and varactor 10 to 20. And you can increase the isolation for your pin diode by placing multiple pin diodes at a distance of lambda g by 4 to increase the isolation. And coming to the switching speed of your pin diode is nanoseconds, MEMS is microseconds, and varactor diode is nanoseconds. In MEMS, it's in microseconds because it's a mechanical switch, so it takes certain time for switching on and off, and that extends in microseconds. And ESD is electronic discharge, wherein for pin diodes it's low, for MEMS it's high, and varactor diode it's low. So you might have experienced this. Sometimes your body is charged, and when you try to touch a metallic body, you get a small shock. That is the electric discharge that we are doing And if this electric discharge happens through these diodes, they are burnt out. So for MEMS, they are highly sensitive to this electrostatic discharge. Then coming to power consumption, because pin diodes are taking current with respect to other diodes, the power consumption is high. MEMS and varactor diodes, it's low. So looking at the characteristics, what we are seeing is wherever you are looking for high isolation and fast switching, you go for your pin diode. You are having uh, high isolation, broad bandwidth, and you can compromise on switching time, then you can go for microseconds, right? With microsecond timing, you can go for MEMS switches, right? So now coming to reconfigurability. How are we modifying the characteristics of an antenna? So here, the characteristics of the antenna can be modified by redistribution of the current on antenna. So you might have seen in some of the papers, they give you surface current density, or they plot the surface current for your patch antenna. The reason why they are doing is they want to show you that they are perturbing the distribution of the antenna surface current, which is leading to desired characteristics. So basically, we whatever reconfigurability that we are going to get, it's happening because of the redistribution of the current on the antenna, right? So how are we going to redistribute this current? We can alter the geometry. Like you can cut the edges of your patch antenna to get circular polarization, right? And or you can make slots on the antenna to disturb the electric current to enhance its bandwidth or get other characteristics, right? Or use external components such as diodes and transistors. So by this way, we can alter the current distribution on the patch antenna or your antennas. So for reconfigurability, here we'll be looking at a few reconfigurable antennas based on switches, MEMS, varactors, mechanical changes that are happening because of actuators, and origami structures. Origami structures are basically the structures which are prepared on or designed on paper. And these are very popular in case you want the antennas to be deployed in space, because whenever you are launching, you want it to be in compact form, and once it is deployed, it can spread out in free space. So for that reason, most of the satellite based systems that they send are based on these origami structures. And then tunable materials wherein liquid elastomers are used, which change their shape. And once the shape is changed, the radiation and the return loss characteristics of that particular antenna are changing. So here, out of all these, the typically or most popularly used reconfigurable structures are with respect to your diodes. And this is done because they have the advantage of low operating voltages, and then the cost and reliability of these diode based reconfigurable antennas is very, very high. However, when you look at these diode based antennas, you require external components to be uh, used. Like you need to bias the diodes, so you cannot directly bias it. You require a bias T to bias the diodes. And then once you are putting your biasing networks, then they may start radiating depending on the frequency at which you are working. And then the complexity of the circuit is also going to increase. So now the typical switches or tuning that we are going to do is with pin diodes and varactor diodes. Wherever you want two states, on and off, or you want two states for your reconfigurability, either this or that, then you go for your pin diodes, which results in discrete tuning, right? You are going to get two states. Whereas when you are using varactor diode, the tuning is continuous because the capacitance value is changing, and as the capacitance value is changing, this varactor diode is loading the antenna, And because it's loading the antenna and capacitance value is changing, the frequency is also going to change, or the overall loading effect is going to change, which results in changing the parameter of the antenna. And then coming to your MEMS, generally we use it, but fabrication of these MEMS switches is slightly difficult. So generally, people who have access to MEMS fabrication go for these MEMS switches. So now we are looking at patch antenna. Here, the central one is the patch that we are having, and then we have varactor diodes and pin diodes placed on this particular antenna. So now, if you are seeing, we are having two groups of antennas consisting of your varactor diodes and pin diodes. So if you are seeing here, these are your diodes, 4 diodes, and we are biasing them through your bias T. So we are applying V1, V2 voltages to these pairs of diodes that we have connected here, right? And then using this, we can tune the frequency in digital form on and off by using the pin diode, or by using the varactor diodes, they can be continuously changed, right? So now, how are we getting tunability in this case, right? So if you see, we are having 3 different states for this particular antenna, wherein the pin diodes, we are looking whether they are forward biased or reverse biased, right? And when we are connecting the varactor diodes, which antennas, which group of diodes are active, right? Based on that, what we are seeing is that we are changing the polarization of the antenna, right? So what is happening when in state 1, pin diodes in group A are forward biased, right? So these are forward biased, so you are short circuiting this and you are short circuiting this, right? And when you are short circuiting this, you are shorting this patch, and that patch is shorted to the ground. So you are providing a ground path to this uh, through your pin diodes that are connected in group A. So when this happens, so when you have considered a square patch here, so the square patch provides you circular polarization, right? Providing where you are feeding the line. So if you are seeing here, the feed is at this point, resulting in a circular polarization. But when you are short circuiting this, the radiation from this edges is the radiation from these edges is short circuited. So your antenna is radiating only through these 2 slots, and hence you are getting your polarization as X oriented polarization. So the polarization that you are having is this way. And similarly, in state 2, you are reverse biasing the pin diodes, forward biasing the pin diodes in group B. So you are forward biasing this and you are reverse biasing this. So because of this, the radiation that is happening through this slot and this slot is short circuited, and radiation is happening through this slot and this slot. So you are getting Y orientation, right? And then in state 3, we are reverse biasing both the diodes. So these are not shorted now. Pin diodes are open circuited. However, because you are having your varactor diodes and all these 4 slots are radiating, you are getting a radiation which is oriented along 45 degrees. So by properly choosing the biases for your pin diode and varactor diode, using a single patch antenna, you are able to get X-oriented polarization, Y-oriented polarization, and a polarization which is 45-degree oriented, right? And this is the response that you are getting, wherein by tuning the varactor diodes, you can also tune the frequency. Not only polarization, you are also able to tune the frequency. So what we are seeing here is you are applying the voltage of 2.2 volts, which results in a varactor capacitance of 1 picofarad. And the resonant frequency that you are getting is here for the earlier patch. So here you are having polarization that is coming because of pin diodes, and varactor diodes are used for frequency tuning. So when you are applying 3.1 volts, the capacitance has decreased to 0.75 picofarad and the frequency has increased. And likewise, when you are applying 22 volts, the capacitance has reduced to 0.15 picofarad and the frequency has increased to around 2.3 gigahertz. So by using either pin diode or varactor diode or both, we are changing the polarization as well as resonant frequency of the patch antenna. This is another antenna wherein this is a monopole antenna which is fed through your microstrip line. On the other end of the microstrip line, you are having a coaxial feed. And here, if you are seeing, we are applying your pin diodes in these regions. Right? Your pin diodes are here, and this figure shows the pin diode. Right? And you are having a capacitor and an inductor, and this line and this line, whatever you are using, is connected to your DC lines. So you are using these DC lines to feed these pin diodes to switch them on and off. So now, if you are seeing here, in case 1, wherein you are taking these diodes, 1, 2, 3, 4, you are having 4 diodes. Based on whether they are switched on and off, you are showing 3 cases here where the bandwidth of your monopole antenna is varying. In case 1, where the switches are open, the antenna is radiating only through this path. When the switches are short circuited, then this part and this part is connected to the monopole antenna. In the third case, the entire flower shaped structure is radiating. So when this diode is on, this structure is connected to this structure is connected to this. When this diode is on, this structure is connected to this structure is connected to this. And when the diodes are off, then only this part is radiating. So that's how you are able to increase the bandwidth of your monopole antenna using your pin diodes. This is another case wherein we are using varactor diodes. So we have a fork-shaped patch antenna and varactor diodes are connected at these points. So basically we are extending the patch antenna or increasing the current flow through the surface current flow through the patch antenna. And then because you are adding the capacitance, the frequency can be varied by varying the capacitance of this particular varactor diode. Right? And here we have bias line where we have a inductor and then that is connected to your bias line. So all these have inductors here. Blue ones represents the inductors. Right? And the feed is provided through your microstrip line. On the other edge, you are having a coaxial feed. So now, by varying the capacitance of your varactor diode, you are varying the resonant frequency of this particular patch antenna. Then we have liquid crystal based antennas, wherein depending on the temperature, the shape of this structure is going to change. So at 52 degrees, we are having this structure. At 82.5 degrees, the structure has changed. It's more or less becoming similar to that of a helix antenna. And at 98.5 degrees, it has further turned. So by varying the temperature, you are getting different structures resulting in different radiation patterns and return losses for the antenna. So these are the responses that we are having for the above antenna for varying temperatures. Then pattern reconfigurability, wherein we are changing the pattern of your patch antenna. So if you are seeing here, you have a main line which is exciting the patch antennas, which is seen here. And these patch antennas are fed through your aperture coupling, and then diodes are used for connecting between the patch antennas, right? And then you have parasitic coupling elements or the tuning stubs, which are used for impedance matching the antenna response, right? So now, if you are seeing here, when the diodes are switched on and off, the radiation pattern is varying with the broadside beam shifting to minus 30 degree. In this case, it has shifted to minus 20. I think this is minus 20, minus 10, and this is broadside radiation. And similarly to the other side. Then this is the antenna that will be simulating using HFSS. So if you are basically seeing, you are having a top microstrip patch antenna, which is your normal patch antenna. On the bottom side, you are having a slot, and then you have diodes here, which are used to increase or decrease the length of this slot line. And whatever you are seeing here, blue ones are the capacitors that are used to stop any leakage, RF leakage happening through these slots that are used for biasing. So if you are seeing here, basically we need to bias these diodes. So in order to bias this diode, if you are not making these slots, you put a positive voltage here, negative voltage here. Without these slots, the diodes are not biased because you are putting the positive and negative voltage at the same potential. So this slot, horizontal slot that we are using, that bifurcates your positive potential and negative potential. And then these slots are used for bifurcating the biases for these 3 or these 5 diodes. So basically, by biasing these diodes on and off, we are going to change the resonant frequency of the patch antenna. So this we'll see at the time of doing the simulation. So these are the dimensions that we are using for the patch antenna. The substrate that we are using is this is Taconic FR RF35 with a thickness of 3.04 mm, permittivity 3.5, and the loss tangent is 0.0018. And then these are the ground dimensions. Now, if you are looking at when you are switching on the diodes and off these diodes, you are having around 9 combinations for these 5 switches. So whatever switches that we are having, central one is S1, S2, S3, S4, and S5, right? So now, depending on the diodes on and off positions, we have taken 9 states here. And if you see, this is the implemented antenna with the capacitors and diodes. And here you are seeing the return loss for the different states. So F1, you are getting the case or the resonant frequency at 3.5 gigahertz. So what we are seeing here is for F1, all diodes are on. So basically what we are doing is, in this particular antenna, all these are shorted. So your slot is not radiating. Only your patch is radiating. So the resonant frequency of this patch you are seeing here. So resonant frequency of the patch is around 3.5 gigahertz. And when all the diodes are off, then we are seeing the radiation of the slot, which is happening somewhere around 2.1 gigahertz. Right? So these are the references that I have used for preparing this presentation. Any queries?
So what about the equivalent circuit, sir?
Sorry?
Equivalent circuit, sir.
Equivalent circuit of?
For the reconfiguration, sir. For the diode model.
That I'll show during the implementation of the antenna using HFSS. How we are going to consider those equivalent circuits, whatever we are showing here. You're talking about these equivalent circuits, right?
Yes, sir.
Yeah, I'll show them how we are implementing them in HFSS during the simulation.
Okay, sir. Another doubt is, sir, how to differentiate the patch antenna from monopole antenna, sir? What is the difference between identifying the patch antenna and monopole antenna?
Yeah, so if you're seeing here, in this case, I have told this has monopole antenna. Reason being, if you're seeing for patch, ground plane will be there beneath this, right? If you are the dark ash color that you are seeing here, that is the ground plane. So for this, for feed line, you are having the ground plane, and beneath the patch, there is no ground plane. So it's like you are having your ground plane over which you are putting your monopole antenna, right? Same thing, your ground is extending only till this point, and this is acting like your monopole. So there is no ground plane beneath your patch antenna, then it becomes your monopole.
Sir, I'm sorry, sir. Please, can you repeat again, sir?
Just a minute. What we are having here, this is the ground, right? So normal case, you have your ground, you have your substrate, and you have your patch, right? So here, this is ground, this is the patch, right? So when you are having ground for your patch, you generally call this as your microstrip antenna, right? But in this case, if you are seeing, I'm having my ground here. Just a minute. Till this point, ground plane is there, right? And this is the substrate. And here I'm having the patch. So this is the microstrip line that I have, and then I'm having my patch here. So this is my patch. If I'm seeing from side, right, there is no ground plane here.
Okay, sir. So for any kind of dimension, if the patch is without ground, then it is considered to be monopole, right, sir?
Yeah.
Thank you so much, sir.
Yeah. Any queries?
Hello, sir.
Yeah.
Sir, how to determine the position where to place the pin diode or varactor diode?
Ma'am, it all depends on the characteristics that you want. As I've told you, if you are looking to modify a particular characteristics, the first thing that we do is we need to see the surface current on the patch or on the antenna, right? So now, as we know, if you are having two orthogonal currents or orthogonal modes, then you are going to end up with circular polarization, right?
Okay.
And if you are having one surface current that is flowing, no orthogonal currents that are flowing, then you get your linear polarization. So now it all depends on how you are changing the current distribution using this pin diode, whether you are able to generate orthogonal polarization, orthogonal surface currents or not. Therein lies your placement of your pin diode. How you are going to, for that you need to understand how your surface current is behaving for that particular antenna. So once you understand
Okay.
your surface current and you know what is required to get the required characteristics, you can modify the characteristics of your surface current so that you get the required characteristics.
Okay, sir. Thank you. And also, I have one more doubt. You will be showing us how to implement varactor diode using ANSYS HFSS.
ANSYS HFSS implementation of your diode is same, whether it is pin diode or varactor diode. Only thing is that if you want to see the tunability on the go, then you may have to use Nexim Designer along with your ANSYS HFSS to see the continuous variation of frequency when you are changing the voltage. But if you want to see at discrete voltages, what is the resonant frequency, with only HFSS, you will be able to do it. But if you want to see the continuous variation, you may have to connect to Nexim simulator or circuit simulator in HFSS.
Okay, sir. So suppose if we want to use varactor diode, we should use Nexim also, right?
Yeah, or circuit simulator which is compatible with HFSS.
Okay, okay, sir. Will you be showing that today or only pin diode?
I'll be showing with the basic pin diode how it has to be done. You can take my mail, and if you have further queries, you please send in a mail. I'll reply back to those.
Sure, sir. Thank
Yeah.
you. Thank you so much.
Suggest some good study material for design and simulation of patch antennas. There is a book called Broadband Microstrip Patch Antenna by Girish Kumar and Professor K.P. Ray. So, wherein you will get very good references, and then they talk in lot about these microstrip patch antennas. Not only enhancing the bandwidth, getting different polarizations, how people have done it. You get a very good exposure to microstrip patch antennas if you are reading Broadband Microstrip Patch Antenna by Girish Kumar and KP Ray. That is a very good book. And coming to your mobiles, we generally use PIFA antennas, planar inverted antennas in our mobiles. How to connect pin diodes with bias circuit. So if you are seeing here, we have connected the pin diodes, and we have used these connectors for applying the positive supplies, and this connector is used for ground, right? So you connect your positive terminal here, and then ground to the bottom copper, and you bias it. But then if you are seeing here, there is a chance that your RF leakage happens through this diode. In order to avoid that, we have a proper bias T. So when I'm saying bias T, so you have an inductor, which is, and then a capacitor here, and you apply your voltage through this, and your diode is connected here. So this is the typical circuit that we use, and your RF line goes in this line. This is RF in, RF out. Right? So your RF line is coming like this. You are connecting with the RF line, your inductor and your capacitor. This part is called as your bias T. So this is the typical biasing network that we use. And at lower frequencies, you can go with this, wherein you are directly connecting. Here you are giving the positive, here you give the ground, right? Positive, this is also positive, and this is also positive. If you want to bias the diode on, right? Hope I've cleared your doubt. So is my screen visible?
Yes, sir. Yes, sir.
Right. So first thing that we do is, if you are not having a original version of HFSS, we go to ANSYS website, we download the student version, install it, and once we open HFSS, this is the environment that we are going to see, and I think most of you might have been using HFSS, right? So now we are going to create a project in this, insert HFSS design, right? What does it say? No license. Can you just give it of 5 minutes? I'll get back.
Okay, sir. Okay. Dear participants, thank you for your patience. We will have a 5 minutes break. Then you can join the session by 7:10.